2 minutes left. Evet, we are host again. Evet. I am looking for the time to start meeting. Okay. Let's start. I am Nurettin Topaloğlu from Gazi University. I and Mr. Bünyamin Ceylan, who is my colleague, will run this meeting together. We are pleased to meet you and very happy to be here. We are sure you will be present very good study and your work. I have to say this. Welcome to meeting.
Hi.
Hajiran, hi.
I am a second speaker.
Second.
Yes.
Yeah.
Between the
wait, please.
Okay.
Second time. This meeting is recorded and broadcasting on the YouTube channel. If you want to see again, you can watch over the YouTube channel. Okay. There is no time to wait. We have to start first presentation. But I think Miss Yasemin Öztekin Çiftçi missed. You can start. Second, Hacire Hanım, Miss Hacire Uğur. Hacire Uğur,
yes.
if you're ready to present your presentation.
Yeah, I'm ready.
Yeah, ready. Okay.
Yeah.
Let's start.
I can share my screen or you can use my recorded video.
Yes, you can share.
Okay. I start?
Okay. You can start.
Yes.
We hear you. Your voice is no. Miss Uğur. Miss Uğur.
Is there any problem for voice?
Okay. No, now it's okay.
Is there any problem or I can continue?
No problem. No problem. No.
Okay, I continue.
Yes, go on.
Okay.
Yes, there is a problem again.
Sorry, I use my recorded video. I see. Is there any problem in that?
Recorded video. Oh.
Yes. If
but
any problem,
we can't hear. We can't hear
okay.
In that time.
Okay, I will do it with live. Isn't problem?
Yes.
Okay.
Please.
Sorry. Now my voice is available for hearing?
Yes, yes, yes.
Okay.
It's coming.
Hi, my name is Hacire Uğur. I am a PhD student at Istanbul Technical University at Physics Department. Today I will talk about investigation of solar radiation power for Ankara province with C# code. First, I'll explain importance of the solar radiation power. Then I'll talk about the parameters which are used to determine solar radiation power. After that, I'll clarify calculation of these parameters with C# code. Finally, I'll justify the result of this study and application of it to Ankara province. Now, let's get started. The analysis of solar radiation data for local region is important because of investigation of,
Your presentation is not seen.
Not seeing?
Oh, yeah.
You are screen sharing, writing.
What? No presentation on the screen.
Sorry.
Select your file.
Yes. This is my file.
No.
You are screen sharing.
No anymore.
Writing in my screen. You couldn't see?
Anyone? Can anyone see?
Now?
No, it's okay. Okay now.
It's okay?
Okay.
Okay, I start again.
Please.
You can see my presentation now?
Yes, yes.
Okay.
We can see.
Okay. Let's continue. For the analysis of solar radiation data for local region is important because of investigation of solar energy efficiency and production potential. Another importance is that by integrating it with digital technological applications will provide high contributions to system builders and operators.
Breaking your voice. Miss Uğur. I can't hear you. Mr. Jilan? Do you hear her?
No, we can't.
Okay.
So I am very sorry.
Maybe sharing video will be good then.
I am here. I am here.
No. Next time, Ms. Çiftçi, next time, please. Miss Uğur? Hacire Uğur? Where are you? I think she's left. Welcome, Miss Yasemin Çiftçi. We can't from you. We can't hear from you.
Now, do you hear me?
Okay, now.
Okay, I am very sorry for late. I have some problem with my PC. I am late.
No problem. You can start.
Okay. Okay. I would like to thank you and chairs and organization committee. And I have already prepared my video because I thought necessary for conference. if you don't mind, I can show my video. I can share my screen.
Yes, please. You can start.
Thank you. Thank you.
Please start after introducing
Okay,
yourself.
Okay, I am. Okay. Before what I do, I have.
No problem, no
Okay,
problem.
okay. I will found Excel. Actually, I sent committee my video, but I don't think it didn't reach. I am sorry.
Maybe
Yeah.
Mr. Topaloğlu.
Okay, I am
Sorry,
trying.
Mr. Ceylan.
Maybe we can share video.
Is there a video, Mr.
Yes.
Çiftçi?
Yeah,
Oh, okay.
I have
I
sent,
can-
but,
I can share the
but
video.
it was long. Before I sent, it was long, and I changed and I rearranged it.
Oh.
If you reach the true one, you can. What I can find now. Please,
Okay, okay. We are waiting for you.
I am very sorry,
No problem.
but actually I prepared, but I didn't find now. Okay, I found it. Okay,
Share full screen, please.
okay.
Hello everyone, my name is Yasemin Çiftçi. First of all, I would like to thank Organization Committee for inviting me and organizing this conference. I am lecturer in Physics Department at Saad University. As our research group, we are interested in the
We cannot see the videos. I think it is opened in the
Okay.
Today I am going to talk about thermoelectric properties of half-star
there's a
nickel,
problem.
scandium, antimony under pressure for energy conversion using abination study. I would like to start
You
with
can use
outline.
share screen
I
again.
will give some
If
basic
you stop the
information
share
about
screen,
No,
Okay, okay. I will.
stop.
you can
Can I-
find and share that one.
Okay, start. Stop.
There is a problem on your screen, I think. You can load again
Okay.
and
Okay.
share the full screen, please.
Okay, I will try. Full screen.
Hello everyone, my name is Yasemin Çiftçi. First of all, I would like to thank Organization Committee for inviting me and organizing this conference. I am lecturer in Physics Department at Saad University. As our research group, we are interested in the basic physical properties of bulk and 2D material by using CFD methods. Today, I am going to talk about thermoelectric properties of half-star nickel, scandium, antimony under pressure for energy conversion using abination study.
Mr. Ceylan, can you see in full screen the presentation?
No, we can't see full screen.
Next, I'll talk about theoretical background and I'll will give the obtained results respectively.
Öyle mi?
What will we do again?
Neler yaptın? Nereden girdin? Ha,
Why thermoelectricity?
tamam.
The world at present is facing the major problem
Şimdi tekrar
related
kapatıyorum
to
o zaman.
energy. One is the energy crisis and another is its environment.
I'm sorry.
You close to your sharing, please.
Okay.
And-
Okay. I am very sorry.
I will share your presentation from my computer.
Okay.
You change.
You have
You change something, but
yes.
there is a problem, as you know.
It was very long before. I don't know what to do. I will if you want, I can-
Try again.
I can
Try
I
again,
can
please.
try again.
Okay, try again.
Share. You are screen sharing. Okay. Full screen. Where is it? Now share. Again, I will open.
You share your screen,
Yes.
not full your presentation. We see in your files and directory and computer concept,
Okay.
not presentation.
Okay, I will open again.
Okay, select again and share.
Share. Stop share. Now sharing. It's okay?
Share screen. No, not okay.
Hello everyone. My name is Yasemin Çiftçi. First of all, I would like to thank the organization committee for inviting me and organizing.
I was panicking.
Don't panic, please. Don't panic.
Oh, no.
Mr. Topaloğlu, maybe you can share. It's better than this.
I think so. I agree with you. But something was
Yes,
changed
I changed
on the
it.
presentation.
I changed it and I also sent, but I am not sure it was true one you have.
I don't know.
How can I?
Please
stop sharing?
close your
Okay,
presentation.
close. Okay, close it.
Okay.
And again, I can try share screen. Sorry, I have a. Efendim?
I am sorry about that, my colleagues. We can't start. I think I have lost your presentation. Can you see your presentation on the screen?
Yes, we can see.
Ms. Çiftçi. Do you share or not?
major problem.
I will close it, please. Pass order, and I will try again. Please pass the order, speaker.
Okay, okay. Who's ready?
I am very sorry.
Michael?
I am very sorry. I am very sorry.
Miss
Yes.
Hajire Uğur.
I'm ready. Sorry for
Okay,
connection.
okay.
I have a connection
You can-
problem.
You can
Yes.
start, please.
Okay.
One of the potential ways towards addressing this problem. Therefore, sources of fossil fuel are
Now you can see my presentation, my screen.
Yes, yes, we can see.
Is there any problem?
No problem.
Okay.
But-
I start.
But second sound is there.
May I start, Chairman?
Yes, yes, please.
Okay.
It is,
Hi again.
it is seeing good.
Okay.
Yes,
okay.
please.
My voice is good. Okay.
Good.
I will start. Thank you. Hi again. My name is Hajire Uğur. I am a PhD student at Istanbul Technical University Physics Department. Today I'll talk about investigation of solar radiation power for Ankara province with C# code. First of all, I'll explain importance of the solar radiation power. Then I'll talk about the parameters which are used to determine solar radiation power. After that, I'll clarify calculation of these parameters with C# code. Finally, I'll justify the result of this study and adaptation of it to Ankara province. Now, let's get started. The analysis of solar radiation data for local region is important because of investigations of solar energy efficiency and production potential. Another importance is that by integrating it with digital technological applications, will provide high contributions to system builders and operators. The motivation for us to study with this topic is that the analysis of solar radiation data will provide to benefit from solar energy better. For this reason, solar radiation parameters were calculated one by one using equations and with C# code for Ankara in Turkey. Sunbathing time, sun angles, solar constant correction factor, declination angle, solar hour, and extraterrestrial solar radiation were explained and calculated with C# code for Ankara province. Now, I would like to explain the parameters which are used to in calculation of solar radiation. First parameter is solar constant, which is defined as the rate of solar energy at all wavelengths incident on an unit area uncovered normally to rays of the sun at 1 astronomical unit. Instead of solar constant, to call solar factor is more accurate because of to alternate slightly a 0.5% over periods of years. The value of solar factor, which is determined based on the results of over 25,000 measurements, is determined by the World Meteorological Organization and recommended the revised value. This revised value is 1,367 watt per meter square. Instead of this, it is adequate to define in SI energy units, and this value is 4,921 kilojoule per meter square hour. This recommended solar factor value is deviated standardly 1.6 watt per meter square and largest plus or minus 7 watt per meter square. Solar radiation onto the Earth is calculated based on the solar radiation outside the atmosphere, which is also called extraterrestrial solar radiation. The eccentricity correction factor of the Earth's orbit is used in the calculation. The formulation of this factor, which is based on Fourier series expansion of Sun-Earth distance R, is developed by Spencer as shown on slide. In this equation, capital gamma is defined as day angle in radians and formulated as shown. Dn in this formula represents the day number of the year, varying from 1 to 365. The C# code, which is used to obtain this parameter, is shown on slides 8 and 9. The Earth rotates around Sun axis, which named as ecliptic plane. The Earth's polar axis, which is defined as Earth rotation axis, inclined approximately 23.5 degrees from the normal to the ecliptic plane. Solar radiation change seasonal because of the fact that the angle between a line joining the centers of the sun and the earth to equatorial plane changes every day, in fact every instant. This angle is called solar declination, which is another important parameter for calculation of solar radiation. Solar declination angle is 0 at the vernal and autumnal equinoxes and has a value of plus 23.5 degree at the summer solstice, minus 23.5 degree at the winter solstice for the northern hemisphere. Solar declination angle is also formulated by Spencer as shown. Solar declination C# code is presented on this slide. The angle that the radius joining a point on the earth to the center of the earth makes with equatorial plane is called latitude angle. It ranges from 0 degree at the equator and plus 90 degree at North Pole, minus 90 degree at South Pole. The solar hour angle, which is an expression of time, is defined as an angle between the longitude of the sun's rays and the longitude of the considered region. The solar hour angle is 0 at solar noon and negative for before solar noon, positive for after solar noon. At sunrise, solar hour angle formula is shown. Sunset solar hour angle formula is the same, except there is minus sign in front of arcosine for sunset. To find the full daily sunbathing time in our unit, the day length formula is used, which is easily computed using solar hour angular formula as shown. Since 50 degrees corresponds to 1 hour, we multiply it by 1/15. Multiplication with 2 corresponds to before and after solar noon. The angle between the sunlight and the vertical of the horizontal surface is called zenith angle. And this angle is defined with trigonometric relation between the sun and horizontal surface of a geographical position. Solar altitude, also called solar height or solar elevation, is defined as an angle the sun rays make with the horizontal surface, formulated on this slide with respect to zenith angle. Zenith angle and sun elevation angle are complementary to each other as shown on formula. Solar azimuth angle is an angle between the clock rotation deviation of the sun rays relative to the north. After a brief explanation of parameters which are used to compute extraterrestrial solar radiation, the C# codes which have been written to obtain these parameters have been shown on these slides. Using the formulations which is mentioned in the methodology part, solar radiation parameters calculation were made in Excel and with the Windows application created using the C# programming language, and data is summarized in this table. Using the data, which is seen partly on a previous slide, distribution of the angle of the days according to the months, figure was formed, and it was observed that the daily radiative power per unit surface exhibited a Gaussian distribution with maximum peak values in summer. This is an expected situation considering the northern hemisphere. This result was expected for Ankara, Turkey, since the country is located in northern hemisphere. The distribution of all parameters and extraterrestrial solar radiation by months for Ankara province is as expected, which is seen in the 3D graphs also. Additionally, in order to examine the consistency of the data, consistency checks were made by comparing the information obtained from meteorology with the program outputs. As a conclusion, we observe that C# code is working very well with high accuracy as shown in the figure. To sum up, as a result, using the formulations, solar radiation calculations were made in Excel and with Windows application created using the C# programming language. And consistency check of data was made by comparing the information obtained from meteorology with the program outputs. The differences between the data are from 0.04 to 0.56. High accuracy evaluation also can be seen in figure 6. This study is used for future studies in creating solar calculations of other locations. Thank you for your listening.
Thank you very much, Ms. Hajira Uğur.
I stop
For
my
your-
share. If any question, I can take questions.
Okay, okay. Is there any question? Everyone. Okay, you can ask if you any question over the YouTube channel,
Okay.
please. Thank you very much.
Thank you for
Yeah.
your inviting me.
Thank you. Bye.
Bye.
We compare that
Miss-
to functional theory with conductive equation. They are equivalent formally, but for similar
Stop your
equations,
presentation sharing, please. Ms. Uğur,
This is
Stop.
not my. This is not my voice, dear chairman. My presentation is.
who is?
I am very sorry. Okay.
Is there any problem, Ms. Çiftçi? Ms. Çiftçi? Do you hear me? Okay. Are you ready, Belgin Koçak? Miss Belgin Koçak.
I'm ready, but also I have a connection problem. Can you share my video?
Okay, okay. I will share your presentation. Wait a minute, please.
Optical properties of yttrium nickel bismuth half-wave star alloy. Ternary half-wave star compounds with a valence electron count of
Mr.
18
Gilan,
per unit
is there any
cell
problem?
and narrow band gap at the Fermi level are in
Everything is
focus
okay.
of researchers due to the promising application of optoelectronics, thermoelectrics, and spintronics. Special interest has been drawn to the red Earth half-wave star containing systems. However, in spite of their significant importance of these compounds, there are very few reported studies on the structural and electronical properties of yttrium nickel bismuth compounds in F43M space group. The aim of this work is to provide a systematic theoretical study of elastic, optical, and vibrational properties of the title compound using density functional theory calculations. The total energy of the electronic structure is calculated using the density functional theory as implemented in the Vienna ab initio simulation package within the PBA approximation. The elastic properties have been estimated with the stress-strain method. Phono-picot has been used to calculate phonon frequency. For the analysis of vibrational properties, the supercell approach has been used to calculate the phonons, and 2 times 2 times 2 supercells. The optimized parameters were calculated by the minimization and full relaxations of the unit cell. It is found that the obtained lattice constants are in good agreement with the experimental result. The calculated electronic band structure result shows that the title compound is in a direct band gap of 0.132 electron volt with the conduction band minimum at high symmetry point X and valence band maximum at the gamma point. These compounds are dynamically stable in considerate phase because they do not have any negative phonon frequency. Elastic properties of a material provide a useful information about their hardness, mechanical stability, and dynamic properties of a material. Unfortunately, there was no experimental determination in the literature of the elastic constants of this compound. It is found that our obtained elastic constants obey the Born stability criteria. So, it can be concluded that the considerate phase is mechanically stable for title compounds. The analysis of the elastic constants enables us to bulk modulus, Sharp modulus, Young modulus, and Poisson ratio. The computed results of elastic properties are also listed in Table 3. The optical properties such as frequency-dependent dielectric function, refractive index, extinction coefficient, reflectivity, and electron energy loss function spectra are estimated in a wide energy range. Briefly, the results in this work can provide detailed information and valuable reference for further experimental work. Have you any questions?
Okay, I think the video is finished. Is there any question to Ms. Koçak? Is there any question? I think there is no question. Okay, thanks, Ms. Koçak. Is there any ready speaker? Is there any presenter? Ms. Topaloğlu,
Okay.
the presentation is finished. Then we can go on.
Mr. Ceylan, my handle give you to take presentation, please. Okay?
Okay, okay.
You are ready. Next, Ms. Irmak
Yes.
Balbuncu is waiting for presentation.
Hi, we can see you, but we can't hear you. Okay.
Thank you. I am a Gazi University PhD student. I am studying with Professor Dr. Ziya Merdan.
Okay.
I sent to video.
We will share video. But can you share your video? Because we can't.
Okay.
I can't because Mr. Topaloğlu didn't leave me.
I don't find. Hocam benim daha sonraydı aslında. Ben bakmak için girmiştim. Özür dilerim, bekletiyorum.
Okay.
Çok özür dilerim. Okay.
Can you hear voice?
Yes.
No voice. Dear professor, no voice.
No.
Okay, I am trying to solve the problem.
Okay.
We can't share your.
Dear professor, the problem will continue as you speak without the handset. Because
Okay.
it needs to use your computer voice.
Trying, but we can't. Same as system audio sleeve. Let's switch to phone audio.
Dear professor, are you the administrator of the system? Did you, Professor Nurettin, give you management?
Okay. 10. I can't share voice. I can't share them.
Dear Professor Nurettin.
Hello, my name is Uzuma Kwamumji. Welcome to my presentation. I'm a PhD student at Gazi University. Today I will talk about the hairstyle compounds. First, I will explain why hairstyle compounds look at multiple properties of palladium to manganese having full hairstyle compounds. Hello, my name is Uzuma Kwamumji. Welcome to my presentation.
Can you hear the voice?
I'm a PhD student at Gazi University.
Yes.
Today I will talk
Okay.
about the hairstyle compounds. First, I will explain why hairstyle compounds is important. Then I will talk about advantages of hairstyle compounds. After that, I will explain some information about bond structure, magnetic properties, this compound. Finally, I will explain this compound behavior and electronic and magnetic properties of palladium to manganese having full hairstyle compounds. Now let's get started. First, principal studies of structural, electronic, elastic properties of palladium to manganese having full hairstyle compounds. First, I will talk about media program. Media is both a method and its computer program implementation to perform efficiently electronic structure and initial molecular dynamics. How to run media? First, we will choose atoms of palladium to manganese sodium compounds from periodic table in media. The latest parameters belonging to the atoms of palladium to manganese sodium compounds were recorded in the second step. Then we will prefer bond structure and density of states from the properties for this compound. For the plane wave basis, the kinetic energy cutoff value has been took 500 electron volts. Now I will talk about the hairstyle compounds. The hairstyle compounds were discovered first by Frederick Hairstyle in 1903. The hairstyle compounds, which are ternary intermetallics, are especially remarkable material on the thermoelectric and spin electric application. There is two types of hairstyle compounds, which are called half hairstyle and full hairstyle compounds, which are given XYZ and X2YZ general formulas. Here, X and Y belongs to translation elements, while Z is the main group element. In this part, I will talk about material and methods. The first principal calculation of palladium to manganese thallium compound was performed by applying density functional theory technique. This calculation was realized with media was tested and the inter-electron exchange corrections was implemented by using generalized gradient application. Figure 1 shows the schematic representation of compounds. The total energy associated with the volume values in the cut-off energy are shown in Figure 2. In Figure 2, numerical values of the volume are obtained by corresponding minimum energy values. The total schematic mass and static parameters of palladium to manganese thallium compounds were obtained 4.40 Bohr magneton per formula unit and 6.478 angstrom respectively. In these cases written by Gibson, all the lattice constants and magnetic moment are calculated and these values that are taken as reference for our study. Then the values calculated for the magnetic moment and the lattice constants are in agreement with literature. The elastic constant depicts that the responsible of the crystal to external forces and examine the critical factor and determine the strength and resistivity of the materials. The Bohr stability criteria of cubic crystals for cubical structure, the elastic stability combinations have the following equation. The elastic constant shear modulus, P divided G ratio, Young modulus, anisotropy, and Poisson rate of these compounds were given at table 2. This ductile behavior of solid can be determined P divided G ratio. If the calculated P divided T ratio is greater than 1.75, the metal is ductile behavior. Otherwise, the metal shows brittle behavior. According to values to calculated P divided T ratio for this compound is greater than 1.25. This which is the critical value, so this material is ductile. Figure 3 shows the atomic total density of states of these compounds. In Figure 4, the total density of palladium to manganese thallium full hexyl compound and atom projected dose. According to Figure 4, this there is no energy gap around the Fermi level. Palladium to manganese thallium compound has a metallic nature. Figure 5 shows spin path structure for the spin up and spin down states of these compounds. To knowledge the structure of a crystal bond has played a major role in determining the many characteristics of the material, such as mechanical and magnetic properties, optical properties, structural deformation caused by electronic properties, and electronic conductivity. As demonstrated from the Figure 5, there is no forbidden energy range at Fermi level. Therefore, it be inferred that palladium to manganese thallium compound shows a metallic character. The total and atomic magnetic moments of this compound were given in the Figure 6. It is clearly seen the result that the biggest contribution to magnetic moment came from metal manganese. The hexyl compounds are remarkable materials on thermoelectric and electronic application due to covalent growth on top of the combinational semiconductors. All these combinational results point out that palladium to manganese thallium compound is a metallic ferromagnet. So far, experimental and theoretical study has not been performed for bulk models, so we could not compare all results with literature. The values calculated for the lattice constant and total magnetic moment are in agreement with literature. Finally, palladium to manganese thallium compounds has been metallic behavior and material shows ductile behavior. Therefore, this compound can be a candidate material for experimental works in spintonic and other applications. Thank you for attention. I hope you enjoyed my presentation. Thank you.
Okay, thank you, Ms. Balmuncu.
Thank you.
You hearing me? I can't hear. Is there any question to Ms. Balmuncu? I think there is no question. Okay, thank you very much for your presentation. And next, Mr. Meguedem, are you here? No.
Miss Agazade is ready, I think.
Okay, Mr. Topaloğlu, if you can,
Hello?
you can go on.
Hello.
You carry on.
Okay,
Share with my video because my computer is broken, camera and microphone.
Mr. Gillan, she is saying her camera and computer is broken.
okay.
Yeah, I joined with my telephone and I trying another computer but I cannot.
With Untitled algorithm. Hello, my name is Sabina. Today I am going to talk about optimal route planning for unmanned aerial vehicle
Are you
in
hearing?
flight restricted zones with Untitled algorithm.
Yes, no problem.
Okay.
Unmanned aerial vehicles are a class of aircraft that can fly without the onboard presence of pilots. Unmanned aerial vehicle consists of the aircraft component, sensor payloads, and a ground control station. They can be controlled by onboard electronic equipment or via control equipment from the ground. Areas of usage and prevalence of unmanned aerial vehicle in the military and civilian areas are increasing day by day. Therefore, it is inevitable that UAV being important in our future lives. In most instances, the use of UAV arises out of necessity. For example, emergency use of UAVs can save lives. In time of crisis, they can be used to transport to hazardous area, water, food and medical staff, and creating communication infrastructure in emergency. UAV path planning is a global optimization problem to generate a set of waypoints from the start point A to the destination point B with guarantee not to fly out of the designed map or being taken by obstacle. One of the problem creating optimal routes for UAV are find out natural and artificial obstacle avoidance. Surely, several devices are used to detect obstacle. However, in some regions, especially in big cities, it is not possible to use these devices. When any UAV are restricted from flying over certain restricted areas. In these cases, must be to pre-plan according to the field map of the UAV flight route. Therefore, It is necessary to determine optimal flight route of UAVs from departure to the destination area, which flight restricted area predetermined coordinates. When there are no obstacle, optimal route is straight line combining from departure to destination area. In this article, to consider reciprocity, all obstacle problem has been solved applying the ant-colony algorithm. The ant-colony algorithm was first proposed in 1992 by Marco Darigo to solve the problem of finding the optimal route. The idea of this algorithm are based on modeling the behavior of the ant colony looking for path to the food source through the anthill. Ants looking for food, they mark the way to travel with a special substance, pheromone. After a while, the pheromone begins to evaporate. The amount of evaporation of the pheromone differs depending on the time arrive and return to the food. The smaller the distance, the sharper and more attractive the smell of pheromone. In this way, pheromone determines the shortest distance for ants. As a result, the ant colony algorithm deals with the problem of determining the optimal route. An optimal route determination for UAVs to go from point A to B by considering the density of building, terrain, complexity, and flight restriction. In this figure, it is decided to create a route from exit point A to B destination point on the map. Rectangles are containing points A and B, and obstacles within the area are marked on the map. The line segment AB has been chosen to be a diagonal of the rectangle. The rectangle starting from point A is divided to m times n square, and L m times n sets are created, which are the coordinates of the centers of this square. It is assumed that each ant can move from one center to another in a fixed time. In other words, the rectangle area is divided into sections according to the distance the ant can move in a fixed time. Suppose that the starting point, point A of the ant is the 0 cell, and the end point, point B, is the M cell. Each cell is shown with two coordinates, which determined according to the position of the rectangle in wind and length. Therefore, assuming the rectangle has M cell in wind and N cell in length, the total will be M equal N times M cells. Suppose there are car obstacles in the area under inspected. Obstacle can have any area. It accepts that each cell has a request coefficient determined by a special rules. It is assumed that the request coefficient of the cells that have intersection with the obstacle are 0. The request coefficient of the cells with the B point are 100, and the request coefficient of the other cells are a random number of selected from 0 to 100. The boundary point of the rectangle are considering as obstacle and given a request coefficient of 0. Thus, we can the m times n dimensional T, I, and G matrix consists of a random number between 0 to 100. Let us donate the rectangle of the rectangle from point I, G to point B with mu sub ij. This amount will show the ants required to reach the target or the attractiveness of the road. At the beginning of the algorithm, the number of ants involved in the process is indicated by k, and the maximum number of iterations is n, and the process is realized in two processes. In the first process, the ant in cell I and G select the next I sub k and G sub k cell. In there, the ant chooses the largest one among the required coefficient of each cell and determines the coordinates of the cell it has selected with the formula. The ant enters this coordinate cell and again enters the cell with the largest required coefficient among the each cell. Around process continue until T I K G K equal 100. T I G are update at each iteration. As a result, roads consist of unbroken lines will be formed by processing the obstacle for each ant. UAV's time to point B will be selected within this pre-given peak point number of broken lines with minimum time for road and the road with minimum length among these roads is selected as the main road for the second process. The second process takes place according to the proposed algorithm with the classical anti-colonial algorithm. To do this, I equal 1 to k G iteration of each E and I and will be represented by three parameters, such as the state G equivalent 1 and t. And the first parameter indicated to the number of ants in the cells, and the second parameter indicator the current amount of pheromone in the cells, and the third parameter indicates whether it is allowed or banned to enter to the cell. At the start, all cells other than I 0 sub 0 and G sub 0 are empty. That is this formula. Number of ants in cell I sub 1, G sub 1 in each iteration. This formula, if cell is selected, we choose this formula, and if cell is not selected, we choose this formula. And at the same time, the number of ants in any cells cannot exceed k. The adaptation process is managed on the ants that choose the I1 and G sub 1 cells in the G iteration. On the other hand, the same station cannot be obtained in two consecutive iterations. In the other words, if the E and I and leaves the cells in the G iteration, then it cannot enter the cell in the G+1 iteration. Initially, in all cells, the amount of pheromone is 0. Thus, in initial case consists of this. From cells I sub k and G sub k to cell L k in the I iteration, probability of passing to one of the 8 neighboring cells. Initially, this is P I K G K equal mu I K G K, and any of the 8 cells are randomly selected. Equation 9 regulates the ant movements according to the obstacle and the fracture line L 0 and 200, and calculates the probability of cell around each I sub k and G sub k. Using formula 9 and chooses the largest of them. The change of pheromone consists when it enters each I cell IK and GK. Here alpha pheromone is rate of evaporation. A calculation experiment has been made according to the proposed algorithm. For calculation process has been developed in C# programming language. For the calculation process, a UAV flight is planned from Street Patrick point A to Service Ontario point B on the City of Toronto map. Google Map application was used in C# programming language. First, by noting the start and end points of the UAV in the Google Map application. This part of the map is divided into small squares. There are 9 obstacles in the scenario created. Obstacles are numbered for further calculation. Considering the limit point and obstacle A, 15, 3 times 33 dimensional matrix was created. In calculation, the number of ants is k equal 8, and the maximum number of iteration is n equal 100. The calculation experiment was carried out in 2 processes. In the first process, the classical ant colony algorithm method was used. And the second process, calculation were made using the method suggested in this study. Here, the red line is the route found with the classical ant colony algorithm, and the green line is the main route found with the proposed algorithm. For both cases, the ants started from point A, and the routes were saved when they provided the necessary requirement. Otherwise, the ant returns to the previous state and the iteration is repeated. If the number of iteration is more than 100 and does not reach point B, the state of the ant will be 0 and the iteration is restarted. During 100 iteration, when provide the necessary requirement on 10 times, reaching point B, the length of the roads are recorded in accordance with this equation, and the experiment continues for the next ants. The results of the experiment are shown in figure 3 and figure 4. In the first process, the dynamics of change of the length of the rod is more constant than the change of the length of the rod in the second process. This is explained by the fact that the second method is more suitable for random selection than the first method. The relative error of the length of rod formed for each method with the main rod is shown in figure 5 and figure 6. First process 78 units, in the second process 72 units. The maximum value of the relative error in the first process was 25%, and in the second process was 13%. Large relative error in the first process is due to the randomness of the selection. In order to compare the result, the average of the relative error of length of the rod formed by the method applied in the first and second process for each and horizontal axis error and the vertical of hand. When the results are
Yani Zoom'da açık, YouTube'da açık. Şuradan şeye bakıyorum.
This means
benimkiler zaten şu notlarıma bakıyordum da.
4% shorter than the previous method. In this article, the problem has been solved by adding a new approach to the classical and colony algorithm. In this article, the main rod, unlike the classical and colony algorithm, is determined by random selection of the ant for achieve a goal without using pheromone. In this process, it is possible to provide for all possible situations, unlike classical colony algorithm. In the proposed algorithm, we can choose large makes it possible to find the more optimal route. Therefore, the proposal algorithm gives 8% better result than the studies with other anti-colony algorithm. Thank you.
Okay, thank you, Ms. Agazade. Is there any question to Ms. Agazade about presentation?
Your student, Ms. Agazade.
Maybe
You have
maybe
to
I
ask.
can see.
You have to ask a question, please. Okay.
Okay.
Next. All right. Mr. Bozkuş is ready, I think.
Yes, I'm ready. Can you hear me? Can you hear me?
Okay, we can hear you.
Hello, everyone. My name is Technology, the Department of Photonics. I send you a video you can run it, and after that I will be here for the question.
Yes, you can start.
I can start or you. How can I share my screen? I don't know. I think you will start.
We can see you. No problem.
Okay, I will share.
You share. Okay. Welcome to my presentation. The title is Parallel-based solution processed wallet with daylight features. Here's the outline. First of all, I will give you some brief information about the OLEDs and some studies, then continue with the materials and device preparation, then results and discussion, and I will finish with a conclusion. Organic light emitting diodes have repeat increase in recent years for space screens and solid-state lighting technology due to their outstanding features including resolution, viewing angle, refresh rate, and color quality. In 1963, Pope et al. First created OLED under vacuum by using a single crystal of anthracene between the electrodes. But there has been an inefficient OLED study that can only operate at very high potential, about 400 voltage. Later, in 1987, first double-layer diode device with separate hole transporting and electron transporting layer was reported by Tang et al. In this study, by using material that transfer electrons and holes and that can work efficiently and works at low potential has been obtained. To achieve an efficient OLED, it is necessary to inject electrons and holes into the emission layer. Confining the electron and holes into the emission layer is one of the most efficient methods. Transferring electrons and holes to the emission layer without comparing them high potential barrier and prevent them from reaching the electrodes and trying to keep it at the center of the emission layer increases the radiative recombination rates and resulting high efficiency. For fundamentals of spin statistic, fluorescence is less efficient than phosphorescence and thermoelectric delayed fluorescence. The reason is that the quantum mechanical formed synclet triplet energy levels have different rates of exciton. Synclet and triplet are formed in a ratio of 1 to 3 for injected charges. So synclet emitter material can only use 25% of injected charges for radiative recombination. However, phosphorescent emitting material can use all injected charges. Phosphorescence and TADF emitter material use rare heavy metals such as platinum or iridium to enable quantum mechanical phenomenon called spin-orbit coupling, which increases the radiative rate of triplet exciton. Displays made with OLED are becoming widespread nowadays. There are many differences between LED and OLED displays, and OLED are advantages in many ways. LED needs color filter, a liquid crystal and backlighting makes them heavy and thick. While LED displays are relatively durable and cheap, OLED displays have many more advantages like color quality, contrast ratio, resolution, viewing angle, refresh rate. OLED have some simple and inexpensive manufacturing method. Spin coating method is one of the most used methods to fabricate an OLED. Coating thickness can be controlled by the concentration and rotation speed. In the previous slide, I said that the phosphorescent materials are more efficient. However, fluorescence material have a significant advantage in white light production. Singlet emitting material have low diffusion length and lifetime. Low diffusion length simplifies device structure and lowers quenching rate. Due to its low lifetime, repeat recombination occurs and high edgestone density in the active layer is prevented. So no color shift is observed and high quality white light can be obtained. We used Perlan derivative as a singlet synthesizer, have a high thermal, optic, and chemical stabilities, and high fluorescence quantum yields and electron affinity and mobilities. There are two important methods for obtaining white light. The first of which is down conversion. In this study by Quadruple et al., a standard indium gallium nitrure blue LEDs were fabricated on a sapphire substrate. Emission spectrum of the device showed a peak emission wavelength at blue region. After coating Perlan dye on a sapphire wafer, the color of the light-emitting diode showed complete conversion to yellow. During LED's working time, the optical transmission of the coating tends to increase. The two graphs at the bottom were obtained under stress test. As can be seen, color shift were obtained and color rendering index are generally low in down conversion, and extra layer may be required to prevent the dye degradation during LED's operation. Three different Perlan derivatives were used as red-orange emission material in the study by Qubit et al. Perlan derivatives were doped into the PVK host and two different electron transport layers were used. Electroluminescence intensity of the blue emission is more in case of TPBI-based device as compared to BFEM-based device. Lower electron injection barrier at the PVK-TPBI interface result in more number of electron injection at the LUMO level of the PVK, resulting more blue emission from PVK. In comparison of TPBI results in a lower electron injection barrier of DPPI-PVK interface, which facilitates more electron injection into the emissive layer, thus resulting in an increased recombination. In this study with TPBI, good enough white light was obtained by balancing blue and orange-red emission. However, gray region of the visible spectrum is missing. This results low CRA and electron transport layer is coated by vacuum thermal evaporation. These are the drawbacks of this study. Materials and energy diagram can be seen at that slide. We used PDI for orange red emitting material and PTE for green emitting material. We used PVK as a host and whole transport material, and two different electron transport material of PBD and OH7 were used to balance the electron and holes in the active layer. Device architecture and coating condition as shown on the slide. Basically, four different active layer configurations were fabricated. First two were used to determine the host and PDI ratio, the third one to determine the PTE ratio, and fourth to optimize the white light properties. According to results, PVK-OH7 host matrix worked at high voltage compared to PVK-PBT host due to the high energy barrier between PSS and OH7. Because of this high barrier, OH7 may have acted as a hole blocking. Although they were utilized with the same doping ratio, PVK-OH7 presented 1.5 times higher active layer thickness than PVK-PBT host matrix. This may create charge accumulation at both sides of the active layer. Electroluminescence maximum of the device with PVK-PBT host presented 15 nanometer of redshift maximum compared to its photoluminescence. The change of two important parameters of white light, namely color correlated temperature and color rendering index, are shown in this figure. Increasing the doping weight percent of PDI in the host matrix resulted in red-shifted electroluminescence spectra and best white light properties were achieved with 0.1 weight% of PDI. As the PDI ratio increases, the electroluminescence from the red region becomes dominant, resulting decreases in both CRI and CCT values. After fixing host matrix as PVK-PPD, green emitting materials of PTE was used instead of PDI. The amount of PTE needed for reaching the best white light properties was much less than the PDI-based device. This indicates a high energy transfer between host and PTE compared to PDI. Just like the case with the PDI-based device, CCT and CRI values decreased when PTE 8% was increased. In order to increase the visible region coverage and enhance the white light properties, PDI and PTE were used together in the active layer with separately optimized. PDI ratio is stable in device 1, 2, 3, but PTE ratio is increasing. However, as can be seen, it doesn't cause a large shift in CE coordinates. However, when the PDI ratio is decreased, the CRI coordinate shift occurs. The main reason of this is that PDI absorbs the PTE emission. By reducing the PDI ratio, this absorption is also reduced and the white light properties are improved. In this way, there is PTE dominated spectrum in device 1 to 3, while balanced spectrum observed in device 4. This device gave CCT and CRI values which are very close to daylight. As a conclusion, in this study we determined the host matrix as PVK-PVD and PDI and PTE dopant ratio were optimized. And to increase the CRI value, we used PDI and PTE together, and finally we reached daylight features. Thank you for listening, and I would like to thank two organization committee members, to my friends from Varlık Research Group, and to TÜBİTAK for project support funds.
Okay, thank you, Mr. Bozkuş. Is there any question to Mr. Bozkuş about presentation?
Yes, I have one question.
Please. Okay.
Mr. Bozkuş, I have just heard BALD. Is it going to be used in the TV?
No,
and
not yet.
Not yet. Okay,
Yeah.
Then when we go to shop center, we have seen some QELD and OELD. What is the difference between them?
Actually, I am not too much information about the QLED, but the main reason is the main differences is the emission layer. They use the quantum dots to emit the lights, and we use the organic materials. As far as I know, this differences is only the emission layer.
Okay, thank you very much.
You're welcome.
Okay, thank you very much, Mr. Bozkuş.
Thank you for listening.
Sorry, if you let me, I can present if we solve the problem.
Okay, Miss Çiftçi.
Evet, yes,
We are listening to you.
Okay, thanks.
everyone. My name is Yasemin Çiftçi. First of all, I would like to thank the organization committee for inviting me and organizing this conference. I am lecturer in physics department at Halk University. As our research group, we are interested in the basic physical properties of bulk and 2D material by using CFD methods. Today, I am going to talk about thermoelectric properties of alpha star, nickel, titanium, antimony under pressure for energy conversion using ab initio study. I would like to start with outline. First, I'll give you some basic information about motivation of the study. First, next I'll talk about theoretical background, and will give the obtained results respectively. Why thermoelectricity? The world at present is facing a major problem relating to energy. One is the energy crisis, and another is its environmental impact arising from conventional ways of utilizing energy resources. The first problem is driving research for alternative energy resources, and the second problem concerns better way of utilizing energy resources. Thermoelectricity is considered to be one of the potential ways towards addressing both these problems. Therefore, the sources of fossil fuel are limited and will run out in future. There is therefore an urgent need to use energy more efficiently and to find other sustainable form of energy, such as solar with high enough efficiency can serve well for both purposes. This annual report evaluated the future development of world energy supply. You can see here the energy consumption rate is increasing together with years. Energy consumption increased very rapidly with years. And what is the thermoelectricity? Thermoelectricity is the basic physical property and is an excellent alternative for converting waste heat into electricity for efficient, environmentally friendly, and maintenance-free cooling system and heat pumps. Thermoelectricity consists of electric current and voltage created through the temperature difference between electrical conductors or semiconductors. Therefore, electrical material generates an electrical current. So, thermoelectricity can meet rising energy demands. Energy has become one of the most searched topics these days. Saving energy and improving alternative energy sources can help to provide energy demand. Statistical results show that in the most of the world, as waste heat, more than 60% of the energy is lost in vain. High-performance thermoelectric materials can directly and indirectly convert heat to electricity. Thermoelectric effect is a phenomenon by which a temperature difference is directly converted to electric voltage and vice versa. Thermoelectric device creates a voltage when there is a different temperature on each side. As you see here, conversely, when a voltage is applied,
What's happening? Ms. Çiftçi?
Sorry, my colleagues, Gökhan Sürücü, play instead of me because I have a computer problem, and so I don't understand why. I think he will solve.
Can directly and indirectly convert heat to electricity. Thermoelectric effect is a phenomenon by which a temperature difference is directly converted to electric voltage and vice versa. Thermoelectric device create a voltage when there is a different temperature on each side. If you see here, conversely, when a voltage is applied, line, first I directly and with round semiconductors. Therefore, an electrical material generates an electrical current. So, thermoelectricity can meet rising energy demands. Energy has become percent of the energy is lost in weight. High performance thermoelectric materials can directly and indirectly convert heat to electricity. Thermoelectric effect is a phenomenon by which a temperature difference is directly converted to electric voltage and vice versa. Thermoelectric device create a voltage when there is a different temperature on each side. If you see here, conversely, when a voltage
Sorry, I think there is a problem with the video.
If you like, I can try again, but I am not sure it is work or not. I played before. I checked video works, but I don't know why it's problem.
You are using MacBook.
I am sorry. I'm very sorry. It was very problem for me. If you like, I also try. If you like. No, I think by copying it was problem.
Next time, please.
Okay. I think not completely download time.
Mr. Ceylan, who's next?
Okay. Mr. Megveddem, Mr. Atacak, Mr. Naife.
Who's ready?
I think
Uh,
there is no one.
Mr. Nafye sent his video. If you let the video, we can see, watch.
Okay, I will share his videos.
Center at Yorktown Heights, New York. It would have been very nice to be with you in person in Ankara. I hope to have some good engagements in the future with you. The title of the talk is Device Design and Integration for Future Computation, both classical and quantum computing. Moore's law showed that basically as you cram more components onto an integrated circuit, the relative manufacturing cost per component goes down. This economic benefit with cramming more components through scaling, when he plotted the number of components per year, he found that it was exponential, and indeed this law persisted for many years going forward and was adopted in the industry as a way to benchmark progress and future roadmaps. Moore's law scaling can be used to use the same circuitry in roughly half the space. So it can be used to lower cost of a microchip, or you can double up the amount of circuitry in the same space. And designers have the option to design using these two concepts to get the most optimal performance and cost. Unfortunately, to develop a leading edge technology like 7 nanometer is quite expensive. Here's an example. It costs $10 billion to $15 billion to build a state-of-the-art plant. This is the Global Foundries facility here in upstate New York. We developed 7 nanometer technology here in support of IBM's microprocessors. Due to the extremely high costs of maintaining this process and doing the R&D work, which cost around $1 million a month, in addition to all the capital costs of the tools and so on, that program was suspended. And IBM now is working with Samsung to provide them with microprocessor chips. Taiwan Semiconductor, to give you a sense of also costs, for 5 nanometer, the costs go up even further. They have promised a $25 billion investment in a new facility in Taiwan to retain Apple's business. Really, the question will be, how far can one go and still have an economic benefit? I briefly described capital costs. So one very expensive tool is the EUV, or extreme UV lithography tool, which is used to write critical features. Shown here is the minimum feature size. The equation goes as k lambda over Na, so it goes linearly with the wavelength. Most features in nanoscale transistors, for the most part, are defined by the EUV lithography, which is argon fluoride, 193 nanometer wavelength. So you can see the EUV is more than a 10x reduction in the wavelength. So it really is a revolutionary step to scale the minimum feature size. The principle of operation is a very powerful CO2 laser is used to excite thin droplets. The resulting radiation from that is at the EUV wavelength. Lenses are used then to focus that beam onto the wafer to write the feature. Unfortunately, this system, due to its complexity, its cost is very high, around $110 million. So that also adds another cost challenge. In addition to the capital gains cost, the high cost, chip design costs are also going up exponentially. This shows a graph of technology versus advanced design costs for a chip. You can see here at 5 nanometer, the cost of designing a chip is around $540 million. And when we go to the 3 nanometer node, due to this exponential increase, the cost of chip design is becoming very challenging to meet. In addition to cost, another major challenge is power. Power density, according to Denard scaling, Bob Denard, who worked at IBM, developed this prescription for scaling, which is called constant field scaling. If one scales all the dimensions, critical dimensions by alpha, where alpha is the square root of 2 or 1.4, power density stays fixed. Unfortunately, that has not been occurring in practical terms. We have not been able to scale the supply voltage by 1 over alpha, but rather by E over alpha, and that's because the threshold voltage is not scaling as prescribed by alpha. Because of this, power density is actually increasing with scaling. In fact, when we go below 100 nanometer node, the power density is approaching the active, which is the passive power plus active power, is approaching the air cooling limit of 100 watts per square centimeter. This high power, which is near the air cooling limit, is limiting the clock speed to be saturated at around 5 gigahertz for microprocessors. Microprocessor power, active power, goes as frequency over squared, and that limits it to around 5 gigahertz. So future microprocessor performance speed advancement, in addition to boosting transistor performance, require system innovations due to this, and that involves single chip multiprocessor, multi-cores, parallelism, and so on. As described, transistor performance will require more innovation versus traditional Denard scaling. So in yellow, the yellow bars here denote the amount of performance improvement due to innovation, while the blue color is the amount due to the Denard scaling. And you can see as we scale technology down further, the gain by innovation is dominating the amount of performance improvement. Innovation meaning, like high K metal gate, and also strain engineering. And let me just describe not strain engineering. This is from our group at MIT from early 2000s. We worked on a substrate strain method where we grow using UHVCVD, a thin layer of silicon on silicon germanium, and due to the lattice mismatch between the two layers, the silicon on top here is under tensile stress, Actually, the amount of stress is quite high. It's around 2 gigapascals for 30% germanium. Because the lattice constant for silicon germanium is higher, the silicon on top is under tensile strain, biaxial tensile strain. And if, looking down here in this figure at the energy diagram, recall that silicon, the conduction band of silicon has 6 conduction band valleys that are degenerate. Due to the biaxial strain, in plane strain, this degeneracy is split between the 4 levels that are in plane and the 2 out of plane. And because of this splitting, the scattering rates are lower for electron transport from source to drain, and hence mobility is boosted. But the key question is, what will happen at nanoscale lengths, like 50 nanometers? Will we still see performance benefit? So to that end, we built transistors in the clean room, looking at, first of all, high doping in the channel to control short channel effects and achieve the threshold voltage required. We also had to develop a low temperature process to prevent relaxation of the strain layer at the top and mixing between the two layers. This is a TEM of the final device structure. Shown here is that the silicon layer on top is preserved. Also, in addition to these low temperature steps, good care had to be taken to preserve the integrity of the silicon surface on top so that a high quality interface between the silicon and silicon dioxide interface was formed, and hence a working gate for the MOSFET. In addition, the layer on top had to be preserved. As you can see here, it's very thin, around 8 nanometers. Specialized cleans had to be tailored that do not etch the material on the top. For example, the well-known RCA clean had to be modified to be at lower temperature to reduce the etch rate before gate oxidation, for example. Shown here is the resulting characterization of the electron mobility as a function of effective vertical field. As can be seen here, the strain data in green versus the unstrained control shows a boost in the mobility for all the doping concentrations in this study. The amount of boost is around 1.5 to 1.7x. However, as one can see here, at higher doping levels and lower vertical fields, the amount of mobility enhancement is reduced. And this was explained in terms of less strain improvement in the Coulomb scattering regime, which happens at lower field. This data was then fit to this Matheson's rule model, which essentially breaks out the regimes of scattering in terms of Coulombic scattering, phonon scattering, and surface roughness scattering. As can be seen here, each component of scattering has a different dependence on the vertical electric field. Surface roughness scattering has a strong dependence, roughly a square dependence. On the other hand, phonon scattering has a weaker dependence, 1/3 exponent. The screen Coulomb mobility is the mechanism whereby, as one increases the gate voltage and increases the inversion layer electron charge, those electrons can screen the dopants, the ionized dopants in the channel, and hence reduce the Coulomb scattering. So that goes up with a vertical field, and then you have an unscreened Coulomb mobility, which is flat with vertical field. So after fitting that model, a nanoscale MOSFET was simulated. Actually, I simulated down to 25 nanometer gate length, and the doping was chosen to have good electrostatic control of the channel down to 25 nanometers. And you can see here the doping levels were very high, as high as 1E19 in the pocket here, halo pocket. So a key question here of this study is if Coulombic scattering, as I showed you before, is if the strain-induced mobility enhancement is reduced in the Coulomb scattering regime. The key question here was, for such high doping levels required for nanoscale MOSFETs, will we still see a benefit or not? In addition to the mobility model, the band offsets were modeled very carefully here. Here I introduced the band offsets in the heterostructure. At the top layer is the strained silicon. You can see the silicon germanium. So for the same gate voltage, due to the band offset here in the conduction band, there are actually more inversion electrons at the surface when unstrained. So the VT is lower for the strained silicon. Hence, to achieve the same VT, you have to either increase the doping of the strained silicon, which adds to the issue of the Coulombic scattering described earlier, or one can use a different work function for the strained silicon to offset this VT. What's shown here is a simulation showing unstrained silicon. This is eye on versus eye off, versus a strained silicon device that has 13% higher doping than the unstrained, and then a strained silicon device that just increases the gate work function. As can be shown here, down to 25 nanometer gate length, significant boost in performance is seen, 30% specifically. And this, these results were presented at the IEDM conference and gave the industry confidence in using strain as a knob to boost nanoscale technology. In fact, we used this at IBM at 90 nanometer, 65, 45, 32, 22, and so on for several technologies. Shown here is the 90 nanometer. We used a tensile strain in the NFET, compressive strain in the PFET. Here the strain was induced through nitride layers on top of the NFET and PFET. So instead of doing it through lattice mismatch as described in the previous study, for 65 nanometer, we had to overcome additional pitch scaling. So we introduced additional strain. So we introduced embedded silicon germanium. And these resulting devices indeed were successful in boosting performance and were used in commercial devices. When we wanted to go from 65 to 45 nanometer due to the ground rule scaling, the experimental data showed reduced performance as we scaled the pitch of the gates. And the amount of reduction was significant, 10% on PFET, 5% on NFET. Basically, physically, what happens is the stressor effectiveness is reduced as this gate pitch goes down due to the smaller spacing. Less volume of stress material can be put in there. And so we had to overcome this pitch scaling issue with strain. To do that at the 45 nanometer node, we combined very high close proximity embedded silicon germanium with compressive stress liner to achieve a mobility over unstrained silicon of 4x. And these two stressors, when combined, boosted the stress at the source side current injection point to a level of around 1.4 gigapascals. So we said pushing strain to the limit. The question then was scaling down to the future was how close are we to the ballistic limit? Shown here are three regimes of operation. One where the length is much larger than the mean free path. One where the length is roughly equal to the mean free path, and one where the length is less than the mean free path. So when the length is much bigger than the mean free path, we're in a regime of diffusive transport. You have a lot of scattering events between source and drain. So we can describe this with the concept of mobility. So if you double your mobility, essentially you double your current. In the quasi-ballistic transport regime, you only have a few discrete number of scattering events from source to drain, while if in the ballistic regime, the carriers just go from source to drain with no collisions whatsoever, so the concept of mobility is inapplicable. So even if we were to boost the strain and get more mobility, we wouldn't see any transistor performance. So to measure this important metric of how ballistic we are, I characterize the injection velocity of strained silicon versus unstrained silicon. And I calculate at 35 nanometer gate length, the velocity is around 9e6 centimeter per second. Comparing this with the thermal limit of 1.5e7 for high strain PFETs, the conclusion was that the ballisticity is about 0.6. So we're about 60% of the thermal limit at 35 nanometer. In other words, there's still plenty of room for boosting mobility and reaping the gains in transistor performance. And indeed, we did that. Now, there was a transition point in the semiconductor industry where we went from strain, and we had to then introduce a new concept called Finfet to achieve the short channel effects necessary at smaller gate lengths. We started with the 14 nanometer process, and then we scaled that down significantly. So we scaled the pitch down, gate pitch by 0.7x. We scaled the metal and the fin pitch by 0.6x, and we scaled the cell height by 0.4x. Because we could not use EUV as described earlier for all the steps, we had to introduce advanced patterning to make the most out of UV. So there are two techniques. One is SADP, self-aligned deposition process. So here, the concept is you start with you have your core patterning using UV. You form a spacer which is etched. We pull out this core pattern. We then use the spacer to etch the critical layer. And so essentially what we've done is doubled the pitch, doubled the density of those layers simply by doing it in this way. Another approach is then to build on this and do it twice. So that's called self-aligned quadruple patterning. So here we essentially do that process twice and achieve 4x the amount of density for those critical layers. So we use this concept. We use to scale from 14 to 7, and we were able to scale our standard cell by a factor of 0.36x, or in other words, that ends up being almost 3 times more computing power for the same area, which is very significant. In terms of the electrical measurements, these are actually high-frequency ring oscillator measurements, and this plotted here is the frequency versus power. We achieved, comparing to our 14 nanometer technology, 40% higher frequency at the same power, or at the same frequency, 55% less power. To achieve those kinds of high ring speeds, we had to improve the device architecture through scaling the fin, advanced junction engineering, contact resistance optimization, introducing novel cobalt contacts in the middle of the line, and introducing a second generation multi-work function that enabled undoped fins and hence high mobility fins. Shown here is the fin enhancements. Here we optimized the fin profile. We used self-aligned quadruple patterning as described earlier to achieve a very nice fin pitch of 30 nanometers. Shown here is the dibble, which is a measure of short channel effects as a function of gate length. So we can achieve for the 7 nanometer node almost roughly 5 nanometer shorter gate length for the same dibble. Next, was the junction optimization. The way we form the junctions in this technology is actually, it's not through implant, but it's through out-diffusing dopants from this epi layer into the channel using a thermal process. So it's through out-diffusion. So this epi was optimized to achieve the best junction possible in terms of short channel effects and also resistance, link-up resistance from the source drain to the channel. And you can see here that, you know, the benefit was quite significant compared to our base process, was 15% by optimizing the epi for that. Next, the interface was optimized to achieve the lowest resistance possible, contact resistance. This did require novel materials at the interface to form the best silicide possible with low resistance, and also the introduction of a shallow implant to lower the contact resistance. The net was a 30% boost in performance. Next, the middle of line contact, the film material was very important. We introduced here a novel material, which was cobalt for this layer. And here you can see we lowered the vertical resistance and horizontal resistance significantly, and this resulted in a lower FET resistance. Next, we abandoned doping the fin altogether. 14 nanometer was using doping. This resulted in very high mobility in our channel, and it also reduced the mismatch, which is the variations between two adjacent transistors due to random dopant fluctuations. The challenge here, though, was how do you offer a full VT suite with no doping? So we had to use the work function to achieve that. We actually, in this technology, offered 4 different NFET work functions, 4 different PFET work functions, spanning almost over 200 millivolts of VT swing. So using this, the designer can use an XVT or very low VT for critical paths where they need a lot of drive current, and they can use a high VT in areas of the circuitry that require low power. Shown here is the mismatch data as described earlier. You can see less variation or sigma VT versus 14 nanometer, comparing the blue here to the orange data. And this is plotted as 1 over square root of WL. This is like the well-known Pelgrom plot for looking at mismatch. So just to wrap it up all together, so future nanoscale electronics in support of classical computing. So, beyond FinFET, we were at the time reaching limits of the fin size. As we were scaling the fin lower to reduce size, we had started to notice performance degradation in terms of due to scattering at the surfaces of the fin. So new architectures are necessary. One promising path is nanosheet slabs. Another one is to achieve even smaller gate lengths is to do a gate all-around nanowire to achieve even better electrostatics. And this can be done vertically or laterally, the nanowire. Another approach to improve performance further is to introduce materials that have higher mobility than silicon in the channel, 3.5s for NFET, germanium for PFET. And then there's also groups looking at carbon-based transistors and 2D materials. In terms of electrostatics, going beyond 60 millivolts of threshold slope, beyond the Boltzmann limit, is being looked at using new physics like tunneling, which has a better slope than 60 millivolt per decade. It's not limited by thermal. And negative capacitance, introducing ferroelectric materials in the high K metal gate. Photonic integration is also being looked at to transmit data from one part of the chip to the other versus using the copper interconnects. This clearly has resistance benefits, power benefits. You don't have all the power dissipation, but it has its own unique challenges of how to integrate the photonic components onto the chip. There's also now a big push on adding or boosting performance for AI applications to do machine learning. And that requires embedding more high performance memory on chip. And then there's looking at more 3D integration, combining logic and memory together instead of having memory off chip, most of the memory. And finally, there are groups looking at integrating sensors, image, chemical, biological with ICs. So now I'm going to transition to a new kind of computing, and we experience the benefits of classical computing every day, as described in the first part of this talk. However, there are challenges that today's systems will never be able to solve. For problems above a certain size and complexity, we don't have enough computational power on the Earth to tackle them. And here's an example of that. The caffeine molecule has 24 atoms. It can exist in 10 to the 48 distinct quantum states or configurations of those atoms. That means for a classical computer to perfectly represent caffeine, it would require 10 to the 48 bits, which is actually close to the number of atoms in the entire Earth. So it's just simply an impossible problem. So it's clear that to solve such problems, a new kind of computing is necessary. So here at IBM, we have a program now to look at to enable quantum computing. Universal quantum computers leverage the quantum mechanical phenomena of superposition and entanglement to create states that scale exponentially with number of qubits or quantum bits. This is, I would like to go through the anatomy of a superconducting qubit. So this is a micrograph of a 5-qubit system on the top. Each box here is 1 qubit, and if we zoom in on that qubit, we see there's a parallel plate capacitor. There's actually a Josephson junction in between. This is the so-called transmon qubit. Zooming in on that Josephson junction, you can see here there's a junction is formed. This is formed through a double tilt evaporation technique using aluminum dioxide, aluminum. The size, the feature size of this junction is 100 nanometer by 100 nanometer. The Josephson junction is a nonlinear inductor, so this enables a distinct 0 and 1 state, as described next. The chip has readout resonators that are capacitively coupled to the transmon. These readout resonators are used to read out the state of the qubit. If the qubit is in the 0 state versus 1, the readout resonator, its phase will shift or its resonance frequency. So we interrogate the resonator through by looking at the microwave transmission or S21 transmission in the readout resonator, and from the transmission we can read out the state of the qubit. As described earlier, so the Josephson junction can be modeled as a nonlinear inductor. In fact, we can look at this system as an analogous LC circuit, parallel LC. At the bottom is a linear inductor with a capacitor. There you get a harmonic oscillator shown here. You can see the Hamiltonian results in equally spaced energy levels, h bar omega. On the other hand, because the Josephson junction is a nonlinear inductor, essentially, these levels have different energy separation, and because of that, this can be used as a quantum system. The separation between 0 and 1 specifically versus 1 to 2, the second excited state, that delta is around 350 megahertz, and we call this the anharmonicity of the qubit. The energy separation between 0 and 1 is around 5 gigahertz, which is actually very good because it's at a microwave frequency, and we have a lot of infrastructure for microwave electronics and RF electronics. So we tap into that infrastructure for our quantum computer systems. If we convert the 5 gigahertz to an equivalent temperature, it's 240 millikelvin. In order to prevent thermal excitation from the ground state to the excited state, we then need to cool these superconductor processors down to a temperature that's roughly 10x below this, which is 24 millikelvin. This then requires the use of a dilution refrigerator, which uses the concept of helium-3, helium-4 mixture to achieve such low temperatures. As described, the Josephson junction is like a nonlinear inductor. The way we fabricate this is to expose a bilayer photoresist with E-beam lithography. The areas that are exposed are then developed, dissolved in a development step. We end up with a Dolan bridge, as shown here. Aluminum is then evaporated with an angle coming from one side and is shadowed by the bridge. We then introduce oxide into the growth chamber to form aluminum dioxide, and this ends up being the tunneling barrier for the Josephson junction. We then evaporate coming from the other side, other angle, at a different angle, and from that we form a junction between the two layers separated by that tunnel barrier. And finally, there's a lift-off step of the photoresist. In order to achieve qubit control, we design qubit control pulses that can essentially rotate the state of the qubit as we need to do. So, we apply, to do this, we apply pulses at the resonance frequency of the transmon, which is around 5 gigahertz. And based on the shape of this pulse in terms of its width and its shape in terms of its Gaussian shape and its phase, we can rotate around different axes, we can rotate different amounts, and hence we can achieve any superposition on this block sphere possible between 0 and 1. So at IBM, we are committed to boosting the quantum performance by 2x per year, and we do this, we measure the performance by a metric called quantum volume. Quantum volume is the largest random circuit of equal width and depth n that the quantum computer successfully implements. So quantum volume is actually 2 to the n. Quantum performance improvement, as we said, we are targeting improving this 2x per year. The best one we have shown thus far is quantum volume 64, which is on our IBM Q Montreal device. And to improve quantum volume, these different threads need to be improved at the same time or commensurately. First of all, the number of qubits has to go up. More is better. The gate error needs to go down at the same time. So more qubits, but error not going down is not good enough for this. So they both have to, improve. Conductivity between the qubits needs to go up to increase quantum volume. And the gate set, as described earlier, so the more number of gates to achieve the rotations described need to also increase. So as described earlier, we demonstrate a quantum volume 64 system. Actually, this is the highest quantum volume in the industry that's been demonstrated. So basically, 64 is, n here is 6. So there are 6 qubit chain. There's a 6 qubit chain with that showed this. Shown here are the gate errors and the coherence values. So you can see here the gate errors are very good, around 7 to 6e minus 3, 5e minus 3. Also, the gate time was tuned down to be around 300 nanoseconds to do this gate operation. And the T1 and T2 times, which are the decoherence times, so T1 was improved, and you can see here the range is 86 microseconds to around 130 microseconds, while T2 is around 78 or 75 microseconds to 210 microseconds. So going forward to increase quantum volume, as described earlier, we need to increase the number of qubits, increase the connectivity. Unfortunately, this is not an easy task. Each qubit has a resonance frequency associated with it. And if these frequencies are too close to each other, or their delta is less than 30 megahertz, we can start to get frequency collisions between qubits or unwanted crosstalk. What's shown in this figure here is in the pink data here is showing the frequency distribution you can see here the spread is quite high, and actually the spread is attributed, most of the variation is attributed to the Josephson junction. So variations in that in terms of its size and so on. And so what's shown in black here is a process where we introduce a laser anneal that can basically shift the frequency as we need. And as shown here, we were able to shift the frequency into 2 clusters. We can achieve these 2 clusters. And in addition to shifting the frequency, this data shown here in black, we enhanced our process to reduce the variations in the Josephson junction. So given these improvements, we can then increase the number of qubits, and also we can improve their conductivity and hence improve the quantum volume without incurring the frequency collisions. The next enhancement knob involves the C0 gate. So the C0 gate is essential to form an entangled state that we call a Bell state. So shown here is a quantum circuit that entangles 2 qubits. And it entangles it in a state that's 0, 0 plus 1, 1 over square root of 2. So 0 would be the state of the first qubit, 0, and then the second one would be qubit 1. The reason it's entangled is you cannot break up this state into 2 different distinct states. You have to describe it in this way as shown here, and then there's a square root of 2 term for normalization. So if one were to measure the outcomes of this circuit, 50% of the time it would be in the 0, 0 state, and 50% of the time it would be in the 1, 1 state. However, due to errors in the C0 gate, we don't achieve that ideal limit. And so a key feature going forward is reducing the error rates of these gates. And I forgot to mention that this H gate here does a superposition. So you do a superposition and a C0. So shown here is that C0 error for different devices that we have deployed. And we have been improving this C0 error, and we have a roadmap to improve it by roughly 2x per year. And shown here is that we can achieve errors well below 1%. As I showed in the Quantum Volume 64 paper, we were able to achieve well below that. And our roadmap prescribes that we continue to reduce this error by 2x per year. The next step involves improving the qubit quality. And the qubit quality the qubit quality depends on the T1 relaxation time. So I'm just going to go through how we measure T1 relaxation. So shown here is the block sphere. We initialize the qubit in the 0 or ground state. We apply a pi pulse, which rotates the 0 state around the block sphere to the 1 state, as shown here. This is through this pi pulse, which is a microwave pulse at the resonance frequency of the qubit with a time duration and amplitude, just right, and we calibrate it to achieve this pi rotation. We then wait an amount of time delta t and measure the state of the qubit. As for a very long time, in the limit of very long time, the 1 state will relax all to 0, and that's what's shown in this graph here. So this graph shows the probability of being in the 1 state. So at 0, the probability is 1 because, we just did the pi pulse. But as we increase the amount of time, you can see the qubit starts to relax. And we fit this to an exponential. Actually, our data is, has a very good fit to the exponential. Chi-squared fit is very good. And the probability at which it drops by 1 over e, we call the T1 time. So that, it's an exponential e minus t over T1. So the goal to improve the qubit quality is to continue to increase T1, and that's done through improving the materials of the Josephson junction, improving those interfaces that are used to fabricate it, and so on. Shown here is an example of such an improvement. We achieved in our dev system a very high quality factor. So quality factor is a concept used in resonators in electrical engineering. So it's just omega times the relaxation rate, omega times T1. So 2 pi times the frequency times T1. You can see here, the systems, that are deployed are, the median is around 3.5 million to 1.5 million. And you can see here that, we have results going out to a median of around 5 million to 8 million. So we have good results in terms of improving this quality factor, but going forward, we're going to have to continue increasing the quality factor, which is a very difficult challenge in materials engineering. So in conclusion, leading edge technology development cost is very high. As a result, Moore's law is not sustainable. Scaling below 7 nanometer requires EUV lithography to achieve the required critical feature dimensions. For a fin technology, that would mean scaling the pitch below 30 nanometers. It would also require contacts to the source drain that are less than 25 nanometers, which would result in very high contact resistance. So the contact resistance is a very big challenge to achieve performance. Technology beyond 5 and 7 nanometer node require new structures to achieve the short channel effects required. Gate all-around transistors and nanosheets are top candidates for these nodes. To achieve AI capabilities, such as machine learning algorithms, high-performance memory integration is required. I showed that quantum computing is necessary to solve problems that classical computing is not capable of. And to demonstrate a quantum advantage over classical computing, we need to continue to increase the qubit number in our systems. And that needs to be commensurate with reducing the C0 error rate, gate error. We need to continue to mitigate our frequency collisions and continue to increase qubit quality factors. And this will require increasing our T1 times from around the 100 microsecond regime to the 1 millisecond regime. Thank you for listening and your attention.
Okay, thanks for this presentation for Mr. Naife. Is there any Miss Yasemin Çiftçi? The problem is there still any problem?
First of all, I would like to thank the organization committee for inviting me and organizing this conference. I am lecturer in physics department at Gazi University. As our research group, we are interested in the basic physical properties of bulk and 2D material by using CFD method. Today, I am going to talk about thermoelectric properties of alpha star, nickel, scandium, antimony, under pressure for energy conversion using ab initio study. I would like to start with outline. First, I'll give you some basic information about motivation of the study. First, next I'll talk about theoretical background, and will give the obtained result respectively. Why thermoelectricity? The world at present is facing a major problem relating to energy. One is the energy crisis, and another is its environmental impact arising from conventional ways of utilizing energy resources.
The first problem is driving research for alternative energy resources, and the second problem concerns better way of utilizing energy resources. Thermoelectricity is considered to be one of the potential ways towards addressing both this problem. Therefore, the sources of fossil fuel are limited and will run out in future. There is therefore an urgent need to use energy more efficiently and to find other sustainable form of energy, such as solar, wind power, and biofuel cell. Among the ongoing direction, thermoelectric converters with high enough efficiency can serve well for both purposes. This annual report evaluated the future development of world energy supply. You can see here the energy consumption rate is increasing ration together with years. Energy consumption increased very rapidly with years. What is the thermoelectricity? Thermoelectricity is a basic physical property and is an excellent alternative for converting waste heat into electricity for efficient, environmentally friendly, and maintenance-free cooling system and heat pumps. Thermoelectricity consists of electric current and voltage created through the temperature difference between electrical conductors or semiconductors. Therefore, electrical material generates an electrical current. So, thermoelectricity can meet rising energy demands. Energy has become one of the most searched topics these days. Saving energy and improving alternative energy sources can help to provide energy demand. Statistical results show that in the most of the world, as waste heat, more than 60% of the energy is lost in vain. High-performance thermoelectric materials can directly and indirectly convert heat to electricity. Thermoelectric effect is a phenomenon by which a temperature difference is directly converted to electric voltage and vice versa. Thermoelectric device create a voltage when there is a different temperature on each side. If you see here, conversely, when a voltage is applied to it, it creates a temperature difference. First event is called is Seebeck effect. Second event is called as Peltier effect. The third one is Thomson effect.
It's off network.
Heat is absorbed or produced when current flows in material with a certain temperature gradient. The heat is proportional to both an electric current and to temperature gradient. This is known as Thomson effect. The most important of thermoelectric application is thermoelectric power generation. Thermoelectric power generation is a solid-state device that provides direct energy conversion from thermal energy into electric energy. The principle of operation is Seebeck effect. Thermoelectric generators contain no moving parts and completely silent. Use of the thermoelectric generators. One of them, harvesting automobile produce waste heat energy, and thermoelectric generator uses this waste heat and convert to electricity. Second one, industrial process waste heat uses to generate electricity. Uses as power sources in satellites and space probes. And last one, it is used for small portable application. Other application of thermoelectrics is thermoelectric cooling. Thermoelectric effect uses Peltier effect to create heat flux between the junction of two different types material. The amount of heat that can be absorbed is proportional to current and time. What is the N-type and P-type thermoelectric material? The heat in heat transport in Peltier module can explain with charge carrier analysis. In thermoelectric materials, charge carrier are electrons and holes. Electron carry a negative charge and holes carry a positive charge. In N-type materials, the charge carriers are electrons, and in P-type materials, the charge carriers are holes. Energy absorbed and liberated can be accounted for by a change in energy level of electrons. Electrons that move to higher energy level absorb heat, and electrons that move to lower energy level release heat. Use of thermoelectric cooling. Thermoelectric cooling is used in electronic, medical, aerospace, and telecommunication. You can see some, for example, in daily practice, there are some advantages and disadvantages of thermoelectrics. The most important one is environmental friendly. No moving parts, so maintenance is required less frequently. There are no fluorocarbons. It is a reliable source of energy. It recycles wasted heat energy. It has long life. And last one is decayability, meaning that the device can be applied to any size heat source from water heater to manufactured equipment. The advantage of thermoelectrics, some of them slow technology progression, requires relatively constant heat source, low energy conversion efficiency rate, and lower coefficient performance than vapor compression system. In this study, we are more interested in thermoelectric material and their properties. So what is the thermoelectric material? A thermoelectric material that can be used to convert thermal energy into electric energy or provide refrigeration directly from electric energy. There are some famous examples having good efficiency. These are bismuth, chalconite, and the telluride. We choose to work with half-Oyster alloys in thermoelectric materials. Half-Oyster thermoelectric materials have been attracting extensive research interest owing to their thermal stability, free of toxic elements, mechanical strength, large thermal power, and moderate dirty parameters. These material systems are potential candidates for medium to high temperature application, which is close to temperature range of most in the industrial waste heat sources. You can see here the unit style of the half-Oyster compound. They have cubic structure. This graph shows how the data parameters showing efficiency change with the temperature for different materials. As you see here, half-Oyster materials have enough efficiency and close orders. If we would like to take a more detailed look at the structure of half-Oyster material, you can see here. Half-Oyster material can be derived by combining troxel and zinc blende type structure. This structure of this material is magnesium, silver, arsenic cubic in space group 216. The efficiency of thermoelectric device can be improved generally by increasing its thermoelectric figure of merit. You can see here formula, where S is the thermal power or Seebeck coefficient, T is the temperature, sigma is electrical conductivity, K is the thermal conductivity, which written as sum of lattice and electronic contribution. So good thermoelectric material have high thermal power, low electrical resistivity, and low thermal conductivity. This can be only achieved in heavily doped semiconductors. Combining high electron density of state with high carrier concentration and high mobility. So we need to increase feedback coefficient and increase electrical conductivity, but decrease thermal conductivity. This work uses theoretical methods. Our method is first principle technique based on density functional theory. The electron density is used in DFT as a fundamental property, which is an observable and can be measured experimentally. If we compare density functional theory with standard Schrödinger equation, they are equivalent formally, but for Schrödinger equation, there are interaction electrons and DFT, there are no interaction constant particles. For Schrödinger, so it is hard to solve Schrödinger equation, but in DFT we use constant theorem and non-interaction constant particle, so it is easy problem. For first principle method, we need only atomic number and crystal structure as the input, which can determine precisely the structure and properties of the real material. Here we can solve the quantum mechanics Schrödinger equation to obtain eigenvalue and eigenfunction, and thus electronic structure and total energy are obtained. Here is the program. Vienna Initial Simulation Package is a computer program for atomic scale material modeling and electronic structure calculation and quantum mechanical molecular dynamics from first principle. Other important program is used here, Bootstrap program. Bootstrap is a program for calculating the semi-classical transport coefficient. The code uses mesh of band energy and interfaces the WASP program and other DFT program. The Bootstrap program uses electrical transport theory. In this theory, it is valid for mean series set longer than lattice spacing, and allows calculation from band structure and scattering mechanism using Bootstrap code. Here, here you can see the conductivity and feedback coefficient formula. Or calculation involve two main steps: optimization of lattice parameter in internal structure, first one, and the second one is calculation of band structure using optimized structure, followed by solving of the Boltzmann transport equation for calculating different transport coefficients. The first two steps were carried out using Vienna Initial Simulation Package. They are based on density functional theory using PAV method. The valence electron configuration, nickel, scandium, and antimony, you can see here, and valence electron count, total valence electron count is obtained 18. Optimizing the lattice parameter and atomic position, we use the 14 times 14 times 14 Montrose point grids. And plane wave basis state cutoff was set to 700 eV for all calculation. But bulk structure calculation, we need to more detailed and more sensitive band structure. So we increase the point mesh grid, because for the calculation of transport coefficient, using Boltzmann transport theory, we need to calculate the velocity as a function of k for different bands. To get accurate value of electronic velocity, it is necessary to have dense K point mesh. Here are the results. I would like to continue with results. We start with crystal structure of nickel, scandium, antimony. This this structure is space-centric structure with space group F33 and magnesium over arsenic. The work of atomic position, and also you can see here. Optimized parameter of nickel scandium antimony, such as lattice parameter, bulk modulus, and derivative of bulk modulus were calculated by minimization and full relaxation of the unit cell, or obtained ground state properties are given in table 1, and energy volume curves for optimized crystal structure is also given in figure 1. To show the effect of the pressure on the unit cell, the structure was optimized at different pressures. The change on the bond length, lattice parameter, and volume investigated and given in figure 2. As a result, it was seen that bond length and structural parameters decreased with pressure. To obtain transport coefficient, we need to calculate electronic bond structure. In particular, we need to know K-dependence of energy bonds in great detail, since the transport coefficient depends sensitively on the velocity of electrons. The calculated bond structure and density state of this compound at different pressure are given in figure 3 for different pressures. It is clear from this figure that this compound is an indirect band gap semiconductor at all applied pressure. Band structures are quite smaller at all pressure. Only band gap increases with pressure. To understand how different constituent atoms and their local coordination control the energy band structure of this compound, total and partial density of states are given in figure 5. Those of system indicate the number of states at each energy level. The participation of the orbital, blue one, in this compound is responsible for creating the band gap. Also, we can say that the electrons of scandium elements play major role in thermoelectric properties. And also in figure 6, electronic behavior has been discussed through the dose for different pressures. It can be seen from this figure that the shape of the curve under pressure have no significant change, showing that structure of this compound is stable and no structural fast transformation occurs the investigated pressure. We have analyzed the valence electron charge density and charge density plots of this compound along 100 plane is given in figure 7 under 2 pressure. Minimum electron is drawn in blue colored and maximum electron in red colored. If you see in figure in this figure, antimony atoms are fairly isolated, and also distribution of the charge is mostly spherical around all atoms. Bonding of this compound has ionic character. When the pressure is increased 50 GPa pressure, the interaction between the atoms increase and the bond length reduce. Therefore, the charge density increases. Elastic constant is defined by the reaction of solid under external forces. By using calculated elastic property like shear, bulk, Young moduli, and Poisson ratio, the stability of the material can be determined. To calculate elastic constant, we use the train method. Obtained results are given in table 3. For mechanical stability, elastic constant should provide for stability condition. According to obtained result, elastic constant of this material is stable stable mechanically even under pressure. According to Octane's anisotropy factor, this material is anisotrope property. And the Poisson ratio is very important property in industrial application. And it shows that interatomic forces in this compound are central forces and have ionic bonding property. According to calculate GB2 ratio, because of near to greater than 0.57 indicating this compound is brittle up to 10 GPa. After that, this compound is ductile. You can see here pressure dependence of the mechanical properties of investigated material. That is, dynamical property become more preeminent property of the material. Thus, the phonon frequency of this compound have been obtained using phonon code. Using density functional perturbation theory, the phonophic code obtained the first constant matrix and phonon frequency. Obtained phonon spectrum graph along several high symmetry directions using 2 times per cell and 24 atoms is given in figure 8 for three different pressures. And there are no any imaginary ones showing that this material dynamically stable under pressure. The magnitude of frequency increases with increasing pressure. Finally, transport properties. We have investigated transport properties for the carrier concentration between 10/18 and 10/20 centimeter minus cube for this compound. Large value of Seebeck coefficient is desired for efficient thermoelectric devices. In purely P-type material, Seebeck is positive, and N-type is Seebeck is negative. The positive value of chemical potential indicates that doping is N-type, and negative value and chemical potential represent P-type doping. Maximum value of Seebeck coefficient is obtained in 250 Kelvin at zero pressure, while in obtained 300 Kelvin, namely room temperature, at applied pressure 50 GPa, which means that this material has good thermoelectric performance under pressure. The maximum value of Seebeck coefficient decreases with increase in temperature. Figure 10 shows the Seebeck coefficient, electric and electrical conductivity, Seebeck S and electrical conductivity at various temperature and two different pressure. More negative and largest value of S reveals that this compound is an N-type material, and very high value of value are found away from the bond edge towards the middle of the gap. It can be seen that peak of Seebeck coefficient are obtained here and here, minus 0.12 and minus 0.01 even. After this value, Seebeck coefficient becomes 0 beyond this point. This implies that this compound will show good thermoelectric properties between this point. The investigated compound have larger Seebeck coefficient at room temperature compared to other temperatures. The other property, electrical conductivity, decayed by relaxation time is an other important factor that influence thermoelectric figure of merit. In given figure 10 also, we found that there is no significant change this parameter with temperature, but is found to increase with increase in concentration in pressure. We see that N-type region has high electrical conductivity compared to P-type region. Note that increasing temperature has no important variation on electrical conductivity for this compound, but increasing pressure, but with increasing pressure, electrical conductivity increase. Thermoelectric power factor is a good indicator in evaluating performance of thermoelectric material. This quantity is proportional to Quebec coefficient square times electrical conductivity. In figure 11, we have give the power factor upper side and that's thermal conductivity with respect to relaxation time for different pressures. Power factor, this compound increases with increasing temperature. Extreme temperature, this compound has maximum power factor for N-type compared to those P-type. This is due to their large of value dose. Lattice thermal conductivity is caused by electrons and lattice vibration. A small value of lattice thermal conductivity means better performance for thermoelectric device. The thermal conductivity contains the contribution for the electronic carrier and phonon vibration. The only electronic part of lattice thermal conductivity can be determined by mean of the Bostrop code. Electronic thermal conductivity is a function of chemical potential at different pressure are given also in figure 11. From this figure, thermal conductivity increases with increasing temperature, and thermal conductivity remains zero at the chemical potential range from in this region is very important for the application of the thermoelectric, or in this region or compound can provide high efficiency. For the thermoelectric device, efficiency of material can be determined by dimensions figure of merit. This also, again, you can see the formula. As the figure of merit ZT greater than or equal to 1 gives the good thermoelectric device. Figure 12 shows the ZT curves of this compound as a function of chemical potential at temperature at the different temperatures and to different pressures. From this figure, we notice that the two pressure material exhibit the same behavior. The predicted upper bound for the figure of merit is about 0.9 at room temperature, which means that the both compounds have good thermoelectric devices. As you see in table 5, the T parameter is at constant pressure decreases with temperature, but at constant temperature, this parameter increases with pressure. At room temperature, the greatest value of data is obtained for 50 GPa pressure and very close to 1. For optimum doping concentration, temperature dependence of feedback coefficient and electrical conductivity under different pressure are also given in figure 13. It is seen that with the increase in pressure, feedback coefficient decrease up to 240 Kelvin. After 240 Kelvin, pressure has increasing effect on the feedback coefficient. Electrical conductivity increase with pressure up to 260, but after this temperature, it decreases with pressure. A final figure depends on the temperature and pressure of the power factor and figure of merit parameters are given in 14. According to this result, pressure has positive effect on the power factor and ZT parameter showing efficiency. As a conclusion, in summary, the electronic, elastic, vibration, thermoelectric properties of this compound were investigated under pressure by first principle calculation. The mixture of heavy and light bonds near the valence band leads to high thermal power and reasonable conductivity. The obtained results show that this compound is stable mechanical and thermodynamically. Theoretical analysis presented here predicts that this compound to be possible novel thermoelectric material with a low value of flex thermal conductivity. As a result, the temperature at which maximum ZT value was obtained when the pressure increases is closer to room temperature. In addition, since the obtained value at ZT is very close to 1, this compound can be used in thermoelectric applications. To sum up, we hope that our theoretical calculated results may provide help to experimentals. These are references, and thank you for attention.
Okay, I am here.
Thank you very much, Ms. Çiftçi. Is there any question? I think we are very tired.
Yeah, I think so.
Yeah, for sitting on the chair for a long time.
Yes, there was a little problem.
No. Okay, thank you very much, all of us. There were some problems, but not related with us. Problem related computer and hardware, I think.
Yeah.
Is there anything to say? I think 2 participants is missing. Mr. Abdulhakim Magadem and Mr. Ismail Atacak are missing. If there is no question, I would like to close the session. I hope that we will meet another conference. Is there any question? Thank you very much, all of you. See you next time.
Thanks.
I'll give you the host,
Thank you.
Gökhan. Thanks.
Thank you.
sorry, Mr. Nafia.
It's okay. I thought my presentation was later in the day, so it's okay. But if anyone has question, you can email me or.
As you see, no more participant.
Yeah.
And we don't want to wait.
I understand.
For a long time.
Understood.
Sorry about that.
No, I think it was the right decision. So, but yeah, it would be good to meet you all, inshallah, in the future. So.
Thank you, Kardeş. Thank you.
Take care.
See you again, I hope. Bye.
It was a good presentation. Thanks.
Thank you very much. Thanks.